If I shout, try and compete with the people outside. But welcome to a brief session on graphene. Has everybody heard about graphene in the room? Anyone heard about graphene? Not heard about graphene? That's probably why you're here. Okay, so I'd like to just introduce a little bit about graphene, what graphene is, what we're doing in the University of Manchester, where graphene was first isolated in 2004, but then start to talk about where graphene is now in terms of different products and applications and what the opportunity might be for the building and the construction area. The aim really of the session is really to start the engagement process, and that taking something that might still be quite early in terms of its development cycle, but has got real opportunity for a number of areas, from construction to aerospace to electronics to biomedical area. If we don't have a chance to cover everything today, we do have a small stand just by the entrance where you can talk to myself or my colleagues after the event. So first of all, the story of graphene. Two scientists in Manchester, 2004, took some sticky tape and a pencil, graphite. They took the sticky tape and the graphite, and if you peel that over and over many, many times, eventually you can get down to a single atomic layer of carbon. So what is graphene? It's a single atomic layer of carbon. It's got length, it's got breadth, but it's only one atomic layer thick. So it's the thinnest possible material possible. And whilst I'm going to talk a lot about graphene today, there's actually now a whole family of other two-dimensional materials that are being developed. Why is that important? Imagine the future where you can actually now design materials into your products or application. Tim from JCB earlier talked about disruptive technology. Imagine if you could design bottom-up, layer by layer, the materials that make your products, whether it's a road, whether it's a battery, whether it's an electronic device, and you could build that multifunctionality into your product or application. What's the potential disruption for materials in that type of area? So having discovered graphene in 2004, what happened? What was the so what? They then started to measure this material, and they found a list of what's been called the superlatives. So for this group, things that should attract your attention are measurements. As a single atomic layer, graphene is 200 times stronger than steel. It's the most conductive material, more conductive than any metal. It's thin, it's flexible, it's transparent. It also can act as a perfect barrier. So as, for example, a membrane, you can either stop all gases or liquids passing through, for example, anti-corrosion, or it could act as a membrane, for example, water desalination. So a whole list of superlative properties that you've not heard about is really why now there's an increasing interest in graphene and 2D materials. And from an academic perspective, one of the most interesting features is really the bottom point, that we're continuing to find new features, new benefits of not just graphene, but a whole family of 2D materials. 2004 was the discovery. 2010, the two scientists got a Nobel Prize. But for me, the more significant event around 2004 is industry started to think about, how do I use this graphene as a 2D material in my product or in my application? The challenge being, how do you go from 2D to 3D and retain some of the properties I showed on the previous page? But again, if you look at case study, look at history, already people are looking at graphene in products from sporting goods, through to aerospace, through to electronics, through to membranes, filtration, through to biomedical devices. So one of the challenges, just talking beforehand, you think of a problem, think of an application, and I could probably say that graphene potentially is a solution to that product or application. So what are we doing as Manchester, the home of graphene, where it was first discovered? We have a breadth of science working on graphene products and applications. So today in Manchester, graphene is international, but as a university, we have over 250 researchers working on graphene. The key message being it's very much a multidisciplinary approach to the science, from physics to materials to biomedical to electronics. More significantly, we've had two significant investments from UK and Europe. We have the National Graphene Institute, £61 million building funded by UK government and from Europe. Why is it significant today? Its business model is about bringing together the academics across the university, but increasingly to bring together industrial partners. And the business model is very much around how do we bring together the academics with engineers, with manufacturing, with industrial people to accelerate the adoption of graphene and 2D materials. I started off by saying 2004 till today, 13 years young. From discovery to today is still only 13 years. If you look at silicon or look at carbon fiber was probably 25, 30 years from discovery into product to manufacture. But what you'll see in a few slides' time already, we're probably twice as fast as carbon fiber, but you're already seeing tennis rackets, Formula One, sports cars, aerospace, and over the next few years, increasingly, you're going to see a number of applications featuring graphene hitting the marketplace. So for me, the message from today is the time is to start engaging now. This isn't just a material of the future, it's a material where now you can start to get some of the benefits from graphene. What I hope to briefly present, though, is a bit like Tim presented earlier. There's linear innovation. By adding a little bit of graphene, we might start to improve the performance. But if we can start to combine the features of graphene, like mechanical strength, thermal management, electrical conductivity, we can start being quite disruptive in some of the markets and technologies and products that we actually take to the marketplace. Beyond the NGI, we have a second building called the Graphene Engineering Innovation Centre. It's fondly called the Geek in the centre of Manchester. It's a bit like the catapults, if people are familiar with the catapults. Whilst the NGI is still a research institute, the Geek, which will be opening next year, is very much around working with small businesses through to large businesses to de-risk and to accelerate the scale-up of graphene products and applications. So I call it a make or break facility. If you think about innovation, you come up with an idea, you come up with a concept, you've then got to rapidly de-risk that, scale it up before you take that into the market. So we're looking to work with HS2 and the partners to see how we might accelerate applications of graphene that may have real benefit or opportunity in the construction industry. So if you look at the program of work, we do everything from making material through to how we measure it, how we assure quality, how we get quality control. But we're also looking at different applications, but very much a business model of collaboration. And today, we have over 80 industrial partners already working on graphene projects. So you're not the first. You'll look at that chart. It's aerospace, it's oil and gas, it's medical, it's large companies, it's small companies. But for me, as an objective, why have we not got more building logos, more building companies that are involved in graphene products and applications? So a quick case study. Graphene is here and now. You can go out today and buy a graphene head tennis racket. 2014 it was launched. It was actually the most successful selling tennis racket that Head have ever produced. 250,000 tennis rackets in the first year. Andy Murray, Djokovic both use it. It's actually a very, very small amount of graphene around the head structure, but by adding graphene into the composite via the resin, what they're able to do is to re-engineer that tennis racket to alter the weight distribution to improve the performance of the tennis racket. Very much a small, marginal gain, but it's starting to show by adding graphene, you can start to tune or change the features of a product. Maybe it's more mechanical strength, maybe it's thermal conductivity, maybe it's starting to combine some of those features to do something different. So where are we now? That was a few years ago. It's quite a lot of marketing. We run an event in Manchester last week where we brought together the graphene supply chain and products. A few years ago, people would have talked about graphene as a black powder or as a film and material. Now you're seeing what potentially is the world's lightest bike. Again, we're now not talking about the features of graphene. The professional cyclist who went on this bike compared to a conventional bike went round a track 7 seconds quicker using the graphene bike and the graphene tyres. Why? The graphene was able to take weight out the frame. By adding graphene into the rubber, you can either improve durability or you can improve traction for equivalent durability. So again, people are already looking around graphene into rubbers, graphene into composites. The far right is a small aircraft with a graphene wing. We flew at the Farnborough Air Show last year, and we're now working with a consortium of aerospace companies from the Airbus, Rolls-Royces, through to small local businesses about how we get graphene into the supply chain of the aerospace sector. Top left is a car company based out in Liverpool. It's still quite niche. Their business model is about track time. So if they can have a car that goes around a track quicker than the competition, any Top Gear fans, that was the fastest legal road car in 2014. That was before graphene. The Stig drove it. It was second fastest, but it had road legal tires. We're now working with them about putting graphene into the composites. So by adding graphene to the resin, to a carbon fiber, I can improve the impact resistance. I can then make the panels of the wing of my aircraft or my bike or my car. I can make it with fewer layers. I reduce manufacturing cost. So again, let's slay one myth, graphene doesn't add cost. By adding graphene a few percent into the resin, into a carbon fiber, I can reduce manufacturing costs because I can reduce the number of layers. I can reduce the cure time. I can reduce the tooling. So one of the key drivers in aerospace is actually the cure time on tooling. So by adding graphene to the carbon fiber tooling, I reduce the cooling time, reduce energy costs, improve throughput and rates. So already people are starting to look about how they add graphene into composites, into resins, into rubbers. So coming to really what I wanted to talk about today, graphene potentially is a solution to everything, but talking to Dave and some of the guys, if you start thinking around building, construction, some of the challenges that you have, one of the key messages I want to really come to at the end is what we really need from you is more of that problem, challenge-driven engagement. We don't really want to understand what graphene does. What we really want to understand is what are your challenges and problems. How can graphene, advanced materials, 2D materials, improve the performance, reduce your cost, improve the benefits of what you're trying to achieve? So from my very limited knowledge of the construction industry, clearly lightweighting is a potential area. So a bit like the car, by adding graphene to the composite, to the resin, I can reduce the number of layers, reduce weight. Why is that important in aerospace? If I could take out a couple of layers from the wing of an aircraft because it's got more impact resistance, I've got an easier safety case to get through, so I can take out weight, reduce emissions, reduce fuel, improve operating costs of that aircraft. Where it starts to get really exciting, going back to the JCB presentation, if I can also combine that with de-icing function, for example, so doing a de-icing function, so move the heat from my engine around the carbon fiber, can I also de-ice my aircraft without that additional cost, that additional weight, that additional functionality? If I can also do lightning strike protection, i.e. if an aircraft gets struck by a lightning, then again, I can take out more weight, improve functionality, improve performance. So in the construction industry, if I can do composites, or is it into the rubber? So again, the work we've done on rubber with some of the supply chain, by adding graphene into the walls of the structure, can I improve flat spotting, tear resistance of the rubber? Can I put it into the tread of the tire to improve durability? We're working with a partner who's claiming potential benefits of up to 20 to 50% more durability for wear on tires by adding graphene into the rubber. Before people say it's new, it's very difficult, the tire industry has been adding carbon black into tires for many, many years. So it's not new chemistry, it's not new processes. By adding graphene, we can start to look about improving the wear or the durability of a tire. We can look about reducing weight. Can I take out weight for equivalent tear strength, equivalent performance? So lightweighting is a key area. Again, if I use my aerospace example, some of the quick wins might be around tooling, might be around weight of tools, weight of equipment, health and safety. If I can reduce the weight of some of my equipment, potentially it may be a one-man carry or a two-man carry rather than a potential health and safety challenge. Heat management has got to be an area of challenge. I know from discussions we've had in the past, this could be everything from de-icing roads through to taking heat in a different way. So rather than having quite complex heat systems, if you go to our stand, you'll see a light bulb, a graphene-enhanced LED light bulb. By adding a film of graphene onto a traditional LED filament, initially we've done that to reduce the energy performance of the light bulb. So a more efficient light bulb by using the graphene to convert some of that heat into light. The byproduct of that was, first of all, we get a more reliable light bulb. There's less stress on the light bulb, so it's a longer lasting light bulb, lower energy, longer life. The more interesting effect for the engineers in the room is now you can start to redesign your lighting product in a different way, because the heat dissipation means, for example, on a conventional LED, you can actually hold that LED. You don't have to worry about the heat emitted, again, for health and safety or other constraints. So you can now develop new forms of lighting, where you actually now have strip lighting, or you don't need the bulb, you don't need the gas. We've also got partners looking at using the same sort of concept for radiators or heating. So now a coating into your paint, or a coating on a radiator, or a coating on glass, you can now heat that structure by dissipating the heat along that graphene coating. So again, opportunity from heating through to lighting, through to, for example, construction. By adding graphene into your bitumen or into your tarmac, again, could you actually change the properties or reduce the cure time so that you can actually use the actual equipment much quicker than conventional drying time for a bitumen. So again, everything from paints through to coatings, through to additives, again, areas of potential quick win. You start then getting a little bit more aggressive, more disruptive, if you like, and start going around the multifunctionality. There's been dialogue around smart concrete. By adding graphene to concrete, could I get rid of the traditional steel reinforcement? So again, there's some work about improving the compression of concrete. Could I actually also make it anti-corrosive, again, for a coating onto steel? I know there's also work about graphene looking at absorbing CO2. So effectively having a lining of graphene in your concrete that might absorb CO2, for example, in a tunnel, being one of the applications I know that people have talked about. Again, some of these are more complex, they're more difficult. They would need sort of collaborative research to take them forward. But through the NGI and the GEEK, we very much look to see how we, first of all, work with partners, but secondly, we see how we really accelerate some of these products to market. Another area that came out of the discussion today that I was listening to was wearables. So again, there's a lot of dialogue around using graphene as a wearable technology. So that's everything from printing flexible screens into your clothing, through to graphene fabrics that might be conductive, through to printable graphene inks, for example, an RFID tag you might print onto your clothing or onto your helmet that might become a proximity warning if your JCB is within 2 meters of hitting one of your workmen. Why graphene compared to silver? Silver exists today. It's quite expensive, it's quite inflexible, it's not easy to wash, it's not that flexible. Graphene's got the potential benefit that it's washable, it's flexible, it's tough, and you can potentially just print it on, for example, like an RFID tag onto your helmet or onto your clothing or onto your structure. So again, these are all potential, but already we're seeing on inks, people are developing the inks, they're developing the printing techniques. The challenge would be how do we develop that into a real product or application that might be suitable or useful for the construction industry. So lots of areas there where graphene can play. The challenge we have, not knowing the construction industry, is which of those challenges are the real challenges where there's a real commercial benefit. How does graphene compete relative to the competition? So why graphene compared to silver as an example? I've just tried to articulate an RFID. A challenge with graphene is getting to the performance of silver, but do you need that performance, or can we enhance the performance of graphene? But can we produce something that's cheap, affordable, and gives you a competitive advantage in your marketplace? So what we're looking for from today and hopefully going forward is to start working with HS2 Consortium, either individually or collectively, to see how graphene might play a key role in this sector. What we bring is that scientific know-how, the academic knowledge. Through the NGI and the GEEK, that's a £120 million total of investment in equipment and facility. But if you think of those two buildings as accelerators, if we continue to work on graphene in a conventional way, it will take us many years to take graphene to market. By working collaboratively with partners from both industry, academia, but also from other people around the room, from investors through to IP lawyers, through to legal teams. There's a real opportunity not just for Manchester, but for the UK. And I was quite interested around the SME engagement. We're particularly focused with the GEEK, which will open next year, about how we create supply chain in Manchester or the Manchester area. But again, we're in Birmingham, so it doesn't have to be Manchester. How do we actually develop competitive product with a supply chain that we can then take to these various products and market? So hopefully got a little introduction of flavour to graphene. As I said earlier, there is a stand straight in front of me by the main entrance. Come and talk to the team. We've got a light bulb, we've got some of the composite panels, we've got some RFID tags, we've got a flexible phone. Again, they're concepts, they're prototypes, but through partnership and collaboration, we can hopefully accelerate those into market. Thank you for listening. Please share about graphene, and please come and see us if you want to find out any more. Just summarising it, this is the journey. I forgot about this chart. This is the summary. We're still very much, if you think of a new technology, it goes on the journey from bottom left to top right. We are an academic institute. The NGI is really pushing the boundary from technology into concept. The GEEK is about scale up, but we want to work with you in industry. So thanks for listening and hope to catch up in the break. Thank you.